In this video, we're going to look at mutually exclusive events in the addition rule. Mutually exclusive events occur when events A and B cannot occur at the same time. So basically, if two events are mutually exclusive, they do not overlap. Okay, so mutually exclusive. So in this example here, aces and kings are mutually exclusive. They can't be both. The two events do not overlap. Whereas if you look at hearts and kings, hearts, there are 13 hearts in a deck. There are 4 kings of all the different suits, but there is a king of hearts. So the king of hearts is both a heart and a king. So there is overlap. Overlap occurs. Okay, so that's what you're looking for, to see if there's an overlap or if they occur at the same time. It could say it's an overlap or they occur at the same time. Okay, so we're going to just decide if two events are mutually exclusive or not. So number 1, is rolling a 3 on a die and rolling a 4 mutually exclusive? That would be yes. A 3 is not a 4 and a 4 is not a 3, so yes, they are mutually exclusive. Determine whether randomly selecting a male student and randomly selecting a nursing major are mutually exclusive. Should be a student. A male could be a nursing student, so this is no. Okay, there can be overlap. There can be overlap, or it can occur at the same time. All right, randomly selecting a blood donor with type O blood and randomly selecting a female blood donor. Well, many blood donors, I would say probably about half the time, will be females, and I don't know the probability of a type O. We can look at that a little bit, actually. But there will absolutely be overlap. So these are not mutually exclusive. All right, number 4, randomly selecting a jack from a standard deck of 52 playing cards and randomly selecting a face card from a standard deck of 52 playing cards. Well, a jack, queen, and king are all face cards, if you needed a refresher on that. And since a jack is a face card, and then they're talking about selecting a jack and a face card, these are not mutually exclusive. So the jack is a face card, so those occur at the same time. And then number 5, randomly selecting a vehicle that is a Ford and randomly selecting a vehicle that is a Toyota. Those are mutually exclusive. So if a car is a Ford, it's not going to be a Toyota, and vice versa. So mutually exclusive events are when the events do not occur at the same time. That's important for us to understand how we're going to use our addition rule for the probability of events A or B. So the probability that events A or B occur is given by the probability of A or B, and that equals the probability of A plus the probability of B minus the probability of A and B. So if the events are not mutually exclusive, we would use this formula here because we have to subtract out the overlap. Otherwise, we are double counting the king of hearts. And that's what is the big idea. So we do not want to double count something, and that's why this equation occurs. Now, if events A and B are mutually exclusive, if there isn't an overlap, if one event cannot occur at the same, if you can't have a card that's both an ace and a king, you don't have that overlap, then you can simplify the formula, and it's the probability of A or B equals just the probability of A plus the probability of B. So that's when they are mutually exclusive. And we can use that to a whole lot of different situations. Okay, so this is different than the last video because now we're just looking at selecting one card. So we are selecting one card, a single card from a deck of 52 playing cards. Find the probability of selecting an ace or a king. So I want the probability of an ace or king. All right, well, the probability of an ace, there are 4 aces out of the 52, plus the probability of a king, which is 4 out of 52, minus any potential overlap. Well, the ace and the king is drawn out up here. There is no overlap. So because these are mutually exclusive, we can use a simplified formula, and we're just going to get, now when you add fractions, you keep the denominator. So we add the numerator, so 4 plus 4 is 8, add a 52, and then we're just going to get 0.154. Okay, and now we're looking at the second scenario for number 7. You select a card from the standard deck of 52 playing cards. Find the probability of selecting a heart or a king. So we want the probability of a heart or a king. Well, these do overlap. There are 13 hearts in a deck. Okay, there are 4 kings in a deck. And there is one card that is both a heart and a king. So if I come over here, these are 12, and then this is 4. 12 plus 4 is 16. And if you look, 13 plus 4 is 17, minus 1 is the 16. So you can also just count up all of the numbers, and it works that way too. It's probably easier to use the formula. So probability of the heart, probability of the king, minus the overlap, so the 1 out of 52, I get 16 out of 52, which is 0.308. Okay, so those are the 2 examples that are drawn out above. Number 8, we just talked about a minute ago. So remember, a jack, queen, and king are all face cards. And I want the probability of a jack or a face card. So probability of a jack or face card. So the probability of a jack, there are 4 jacks out of the deck of 52. There are 12 face cards. And then all of them are an overlap, right? All of them. So you would have to subtract out the 4 over 52. So in a way, I would just say this is really just the probability of a face card. Okay, so when the 4 and the 4 cancel, you're going to get 12 out of 52. So if you can recognize that all the jacks are face cards, you're really just doing the probability of a face card. This, I feel like, complicates it a little bit, but if that keeps it easier for you, then just write the whole thing out. It really doesn't matter. And then 12 divided by 52 is 0.231. Okay, so this is kind of a special case where all of the jacks were face cards. All right, number 9. You roll a die, find the probability of rolling a number less than 3 or rolling an odd number. So again, I would probably look at my total sample space. So find the probability of rolling a number less than 3. Well, that's 1 and 2. And rolling an odd number is 1, 3, and 5. So to keep that simple, your probability is 4 to 6, which is 0.667. To me, when it's kind of a straightforward question like that, I would do it by the sample space. So you could write out the sample space. If you want to use the formula, you absolutely can. So the formula that the probability of a roll of a die being less than 3 is 2 out of 6. Probability of an odd number is 3 out of 6. And then they overlap with the 1. So minus the 1 out of 6 is your overlap. You get 4 out of 6, and you can get it that way too. So this is using the formula. Okay, so there are 2 ways you can do that. Number 10, you roll a die, find the probability of rolling a 6 or rolling a number greater than 2. So let me do it by the sample space. Okay, so rolling a 6, pretty straightforward, it's just going to be 6. Rolling a number greater than 2. So greater than 2 would include 3, 4, 5, 6. Okay, I wrote it twice. So remember I said don't have the overlap. So this is going to be 4 out of 6. We just did this one. So 0.667. If you want to use the formula, by all means, you always can use that formula. Probability of rolling a 6 is 1/6. Probability of rolling a number greater than 2 is 4 out of 6. And then I wrote it. I wrote the overlap. So then minus 1/6 for that duplicate, and you would get 4 out of 6 when you did that formula out. Okay, the last thing that I would like to show you is how to use a table and a two-way table. So finding probabilities from tables, the frequency distribution shows volumes of sales in dollars and the number of months in which a sales representative reached each sales level during the past 3 years. All right, so it took 3 months, 5 months, 6, 7, 9, 2, 3, 1. So we're looking at the sales, total sales, and how long different people took to reach that mark. So that's what they're looking at here. The number of months in which sales representative reach each sales level. Okay. So this is something that you would use if you were a small business owner. So you could say, all right, how long did it take a particular person to get to this level? And now it's saying 3 months. So find the probability that the sales representative will sell between $75,000 and $124,999 next month. So we're going to be looking at this area here, so between 75,000 and 124,999. If we're looking here at this amount, we're looking at all of these. And in order to actually calculate this, we have to look at the total months for this problem. So I'm going to look at the total months. And there are 36 months in total that we're looking at, and the probability of being between 75,000 and almost 125,000 is going to be 16. So I'm going to add those two out of the 36. Really try to keep it simple for yourself and not overcomplicate things, because with the table I feel like the math is pretty straightforward. And then you would just do 16 divided by 36 to get 0.444. The next example, we're looking at between $0 and $49,999. So now we're looking at the first 2 rows of the table up here, the 3 months and the 5 months. So I would do 3 plus 5, and that would be 8 out of the 36. Okay, and when we divide that out, you get 0.222. All right, and then finally, now we're looking at between 0 and almost 50,000, or between 150,000 and almost 200,000 next month. So now you want to look at this section and this section. So between 0 and 49,999 is what I just highlighted in yellow, the 3 and the 5, and then the 150 to almost 200 is going to be the 3 and the 1 over here. So you would add the 3 and the 5, and you're going to add the 3 and the 1. So I'm just pulling numbers off of the table. So again, I'm going up here looking from 0 to almost 50,000, and that's going to be the 3 and the 5. The 150 to the almost 200, and that's the 3 and the 1, and I put those all together. So 3 plus 5 plus 3 plus 1 is going to be 8 plus 4, which is 12, out of our total of 36 months, which is 0.333. So don't overcomplicate questions from the table, because really you can just go up to the chart and read the chart, and hopefully that's straightforward for you. All right, the last kind goes back to that type O blood question that I was looking at before. And I said I didn't know the probability of having type O blood. Well, I actually could find it now that I have a two-way table for this particular sample of data. So we have 409 total people. And up here it says a blood bank catalogs the types of blood, including positive or negative Rh factor, given by donors during the last 5 days. The number of donors who gave each blood type is shown in the table. So if you're not familiar with blood type, you have type O, A, B, and type AB. So there are 4 blood types. And then there are 2 Rh factors, is either positive or negative. So this is a two-way table, so we can look at the blood type and the Rh factor. So a donor is selected at random. Find the probability that the donor has. Now this is one donor. So when you're looking at one donor, we can look at our addition property of probability, okay, our addition rule. So find the probability that the donor has type O blood or type A blood. Well, these are mutually exclusive. There's no overlap. So if you're type O, you can't be type A and vice versa. So we're going to look at our total row here. The type O is 184 out of the 409. The type A is 164 out of the 409. There is no overlap, so there's nothing to subtract here. And I would encourage you to write the total, whether it's the actual total or a subset of the sample space, and use that as your total, and then do your operation in the top. And I think that'll prevent you from making little math mistakes. So when I add the 184 and the 164, you're going to get 348 out of 409. So this is a great number for me to look for because that's the exact probability. And then when I divide those out, I get a decimal of 0.851. So that is a rounded probability. Okay? These were mutually exclusive. The next one is type B blood or is Rh negative. So these are not mutually exclusive. Not mutually exclusive. Okay, so, and we're looking at the total. So there was no given that, so no sample space change or anything like that. So I'm just looking at the total. So there is an overlap because 8 people have both type B blood and are Rh negative. So out of my total of the 409, what I'd like you to do is we're going to look at the type B blood. There are 45 with type B blood. There are 65 that have an Rh negative factor, and our overlap is these 8 folks here that are both Rh negative and type B. So when you make that calculation, when you do 45 plus 65 minus the 8, I'm getting 102 divided by my total of the 409. Okay, and that'll give me 0.249. I'm not going to round up because the next digit is a 3. Okay, the next one, why don't you go ahead and try 16 and 17 if you feel comfortable with that, and pause the video. All right, for 16, type B or type AB blood, these are mutually exclusive. Okay, so then we would just do out of the 409, type B is 45 individuals, AB is 16. So when you add those up, you're going to get 61 out of 409, which is 0.149. All right, and then type O or Rh positive, these are not mutually exclusive. So then we would have to subtract out the overlap. So out of the total of 409, you have the 184 plus the Rh positive, the 344 minus the overlap of the 156. And when you do that out, 184 plus 344 minus 156, you're going to get 372 out of the 409, which is 0.910. So clearly, O and Rh positive, if you're looking at those 2 events, they are very popular. All right, so that's how you would use a two-way table. And then the bottom of this note sheet is a big summary of classical empirical probabilities, the range rule, all probabilities are between 0 and 1, the complement, we've looked at that recently, and then the multiplication rule and addition rule. And you can see the review of independent versus dependent and mutually exclusive versus non-mutually exclusive events. All right, thanks for watching.